Hi, welcome to this tutorial. Today we will talk about Google Global Foundries Open Source Process Development Kit, aka GF180MCU BDK, and how to use it with the open source tools to design a simple CMOS inverter. First, the BDK has a documentation as shown here from this link, which contains all information that will be discussed here. You can find the documentation link in the description along with other useful links like GitHub repositories. Okay, so about the BDK, it has three combined options, A, B, and C. Each one of them will have certain options like number of metal stacks, metal top thickness, and NIM capacitor type. Here we will use the option C because it has all metal layers. We can design full circuit from schematics to layout as the BDK contains all required files like schematic symbols, model cards, P-cells generators, verification files, standard cells, PNR information, technology definition files, and so on. Please note that this tutorial doesn't include how to install the required tools as Xscheme, ngSpice, and klayout, and we assume that they are pre-installed. Moving to the installation section, the BDK can be cloned and we can copy each file in its destination. But this method will take more time and effort. Another method is to use Volar, as shown here. Volar is a version manager and builder of Google open source BDKs. But before heading to the installation itself, some environment variables must be defined. So open a terminal. Okay. We need to open the shell resource environment variables, aka bash rc. So now we need to export our variables. First one will be bdk root, which points to the directory that we need to install our BDK. So I'm choosing home and a directory in it called BDK. Now we need to export the other one, which is BDK. This will choose the flavor of the BDK that we want to use. As we said earlier, we need to select C option. Perfect. We need to save the file, and then to take effect, we can close this terminal and reopen it again, or simply by sourcing it to take the effect we need. To install Volar, head to its GitHub repository, as shown here. Now you can find a list of installation commands that we need to run. First, make sure you got all the requirements before installation. So for installation, you can copy this and use it here. To install Volar. Perfect. Now it is installed, so we need to run some other options. Here, using this command, we can list all available BDKs for the Volar. We will take this and as this is pointing to GF180MCU. As you see here, there are two versions. We need to select the latest and install it. So to install it, simply we can use this command, volar enable --bdk. We will replace Sky 180 with GF180MCU. Sorry, 130. Okay. So GF180MCU. Select this hash or commit ID, then press enter. As you see here, this will be installed, downloaded and installed. So I will pause the video until this operation is finished, then we will be back. Now it's about to finish. You can see here only 2%. After the downloading, it will unpack the package to be installed. Again, I will pause the video until it finishes. Okay, it's about to finish. Done. Now, we can view that we had installed it simply by using this command. GF180MCU. As you see here, this is what we had installed, which is also enabled. Now we can head to schematic drawing. So we can close this terminal. Actually, we need it again. So the tool for this task is XScheme. And to load the PDK inside the tool, a RC file called xscheme.rc should be linked or copied inside the directory that will be used for the design. So first, we need to make a directory with any name you would like. I will choose tutorial. Okay, I already have directory with the same name. Simply I can remove it and make it again. Okay, you can choose any name you would like. Now, I will link the file that we talked about, which is located in PDK root, PDK libs.tech xscheme RC. Now we can run the tool. As you see, I got some error. These errors, we need to solve it. So simply, we will be editing the xscheme RC file. So first, we need to search for xscheme library path. Here, when you see environment BWD, we will change it to PDK root. PDK libs.tech x. Second, we will need to go to the latest lines. As you see here, this line, which calls energy spice models, we will need to convert it to PDK root in PDK libs.tech energy spice. Now we need to save the file, close it, and running the tool again. You see the error is still there because we need to copying two directories. So the first directory will be tests, which we need to make it GF180MCU tests. Second, we need to copy another directory called symbols into this directory with a new name called GF180MCU FDPR. Now we can run the tool again. As we see, we only got warning of overlapping, which isn't a problem, but here everything is running okay. As you see, we got some symbols. If we select some object of these and press E to get inside it, you can see everything is now working. You can left click mouse with control key to view the simulation, and if you want to run simulation, we can use this block, but by pressing Q we can edit this to ng spice, not spice. Press OK and save. Yes. Now XScheme is ready to run. You can press F to fit everything. What we are going to draw here is an inverter. So click on plus sign to start the schematic, then press Shift I to insert the symbols we want. So from the other, we can select symbols. Now we need to get NMOS and PMOS. So we can select PMOS and place here. Press Q to edit its W to 0.44 because we are designing CMOS inverter. So Shift I again, insert NMOS. Okay. These are 3p3, which are 3.3 volt. We can lift the NMOS with its parameters, so the PMOS will be double size of NMOS. Now we need to insert finally Shift I, but this time from home we need the XScheme library devices. We will need IO pin. Okay, because we are going to design a symbol. So we can copy this pin, Ctrl C, Ctrl V, again. We can use Alt R to rotate. Yeah. Now, to wire everything, we need to use W to insert wires. W, 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 W. Pressing W's multiple times to change your direction when creating wires. And by clicking the left click mouse, we'll create the wire. So pressing Q on each of these and change its label to any name that we want. Here would be ground, and here will be VDD. Finally, this will be out. Okay, we can save this design by Ctrl S, current directory, and we need to call this schematic end. Okay, now we need to create our symbol. Simply, we can make symbol from schematic or by pressing A. Okay, now we need to open this file. So open current directory. You see here, this symbol is auto-created for our purpose. Now we need to modify this symbol to look like an inverter. So by removing this and this, by pressing delete and this line and this also, we can move it with N. Now we can put it here and draw another line from here. Insert line. Another line we can draw. Now we can insert a circle to represent the bubble. Okay. Click to this point. This point. Again. Now, bubble is inserted. We can move all of these. This also will be moved. Alt R, move. Finally, this is subcircuit name, and this is our device name. Perfect. Now we can save with Control S, yes, and we can start doing simulation by pressing this plus sign and starting a new schematic. This schematic can be prepared to simulate our inverter. So press Shift I. We need to insert vSource. Okay. Also, we need to insert VDD. Okay. And ground. Okay. Finally, code shown. Okay. We can select code also, but we need shown to see everything alright. Okay. All of these, we will need to duplicate them. So by pressing Ctrl C, Ctrl V, we have two of them. Okay. This can be moved here, and this moved here. This can be moved to here, here. Okay. Finally, we need to insert our symbol by pressing current directory, inverter symbol, click OK, and here is our inverter. So we need to edit these properties. So for this, we will need to press Q and make the value 3.3 to be our VDD. This, we need to remove this and put this double quotes and make it false. Sorry, false from 0 to 3.3 volt, 100 pico delay time, 1550 pico rise time, fall time, full switch and the period. Okay, as you see here. Okay, we need to edit this code and make the value double quotes dot control save all to save all currents and voltages for each node. Tran for transient analysis 3 pico to 600 pico. This is our increment and this is a whole simulation runtime. We need to plot in and out, which will be labeling our wires. Finally, .nc. Okay. Now we need to insert some conditions here, which simply we can copy it from here. Q, take all of these, can select them, Control C, okay, back here, select all of these, Control V, okay, this can be called ngSpice. Now we need to wire everything. Pressing W, W, okay. Now we need to insert wire label from Shift I, Home, Devices. We need label, lib wire, okay. Press 1 here, Control C, Control V, Alt R, here, okay. This, by pressing Q, will be N, and this will be out. Okay, we can save from here or by Control S. Now, this time we can save it as env testbench. Okay, we can create our netlist, then simulate. Okay. So we forget to wire our source, so I wire them, save, netlist, and simulate. Now, as we see here, this is the simulation that we're looking for, and here everything's running fine. Now, we can head to layout drawing. So we can close Xscheme and Control L to start in the layout. We'll be using KLayout for drawing our layout. So to run KLayout, we need to type KLayout home equals BDK root BDK lips tick KLayout -e for edit. Okay, yes. As we see here, we can select GF180MCU. This means our PDK is installed but the drop-down menu isn't there. Also, if you encounter this problem, I'll make a new layout instance. From this, there is no library for GF180MCU. So, if you encounter this problem, close the key layout that we have opened and rename some files, directory called by macros into cells. Okay. Next, we need to make directory by macros. Then we need to move those cells in this directory. So cells by macros. And finally, we need to move a file from tech called GF180MCU.lym to by macros. Now, if I try to open key layout home, file, new layout, okay, instance, library, we can see now we got our library. There's one more thing, the drop-down menu isn't there. So, can close it again, going to MyBrains, Google Foundries. This repo should have been merged, but till now it isn't. So we go to drop-down menu. We will see here, this is a repo that includes the drop-down menu. We can clone it by copying this. And here we can get clone, the repository. I will pause the video until it finished, then I'll return back. Now, after it's finished, actually I have stopped it and copied it from my side to make it faster. So, all we need to do is to copy a directory from the repository rules, key layout, macros, to key layout. Okay, now we can reopen key layout. This time you can see the drop-down menu for GF180MCU, which we can run DRC and LVS and load options for them. Now, let's start drawing our layout. So by going to File, New Layout, we can rename our top cell into N for inverter, and our unit database should be 5 nanometer to mitigate some DRC errors, and click OK. Now we can start inserting our cells from editor option. Okay, now we can select the cell, which can be NMOS. Okay, and from P cells we can use our options. So we don't need deep in well, neither it's guard ring. We need a bulk tie and the minimum size. Okay, we can now drop it here. we have actually placed an NMOS MOSFET. Now we need to place PMOS also, so head to PMOS. Okay, from P cells we don't need deep and well, laser card ring, we need bulk tie, and the width we need it double, and everything is fine. Make sure when you draw this, we need the PMOS a little far to the NMOS to mitigate some DRC rules. Okay, now to see the cells that we have placed, just make this 2, or simply by click this. Now we can see our PMOS and NMOS. Let's try to wire them. So wiring them is truly easy. You can click here and hide in the layers. These are our only layers that are drawn. So we need to draw wires by selecting this metal, and from box we need to start drawing. But first, let's make them aligned. We can move now they are aligned. We get to the gate. We can from edit selection move by y -1. Okay, that's great enough. Now we can start drawing metals from box and draw metal from here, another metal here, from source to the bulk. Those are 2 drains, and from source of NMOS to the bulk also. Finally, we need to draw poly. This time we need to make sure they are aligned. So, sorry. And here we go. Perfect. Now I need to add some poly to the output, or input, I'm sorry. So, can just copy this that I had created, Control C, Control V, edit, selection, rotate. We can move, edit, selection, move by -half. We can select partial to make it more longer. Now we can insert a box with poly here, and this box we need to insert some contacts. So we can access one of them by show as new tab. Now we need to select metal and the contact. Okay, this won't be selected because we are not flat. Okay, no problem. We can return back. So we can insert a box of contact from here, draw something like that, and select it, press Q. Now we need its size to be 4.22. Okay, perfect. Now we need another box of metal one box. This time, by pressing Q, we need it 0.5 to 0.5. Okay, now we're ready. So we need to insert some labels. So we're returning back from empty layers to select little one label, make it shown, and now click on text. Let's start by writing VDD, which can be placed here or here. GND, which can be placed here. Out, here, and finally in here. Now we can save our layout by pressing File, clicking File Save. We can name it in.gds. That's it. Now we are ready to run DRC and LVS to check if our design is clean or not. Okay, now before we're going to run DRC and LVS, there are some tweaks we need to do before it. So head to the terminal, a new terminal. Okay, we need to copy some files from the repository. So we can take this, here. This time we need DRC, we need each file that ends with .drc into klayout DRC. Okay. Yes. Now we need the same thing for LVS. Okay. Now there is one more thing we need to do before going into. We need to run xscheme again directly to our inverters that we had created. Okay. Now we need to click on simulation, check LVS netlist top level is subcircuit, and uncheck use spice prefix attribute. Now click on netlist and close xscheme. Now we need to copy the file that had been generated from .xscheme simulations inverter with spice here. We need to rename it from in spice into inf.cdl. Finally, we need to open it. So this looks perfect to be run, but we need to remove all these equations. So I'm going to remove this and these, and saving, close. Now turning back to klayout, we can run DRC. But before that, we need to go to macros, and from macros, we need these options to be refreshed. We need to make sure everything is available. Now we can run. So we can run DRC. These are options. We can run the DRC right now. I will pause the video until the DRC checks is finished. Now, as we see, the DRC is about to finish. It's finished, and as you see here, we got 3 errors. We can explore them. As we see, this poly needs to be a little bit further than this, okay? And this contact, you need to check this, okay? Okay, let's close this and solve these problems. First, this, oh, it was made by P+, not a poly. So we can select poly here, and from edit, selection, change layer. Now become poly. So all our problems should be solved. We can now save, file, save, and we can run DRC again. I will pause the video until it finished. The second DRC run is about to finish, so we're ready to view the results. Nice. This means our cell is clean from DRC errors. Now we can head to the LVS. So for LVS, we need to set an option of substrate name to be ground. Okay. If there isn't any message box that appeared, we can go to macros, Ruby, LVS, click right and refresh. Now this should be passed as we had made. Now we can run LVS. Again, I'll pause the video until LVS's running has been finished. Now it is finished. We can see the results here are clean. We can explore pins which are correct, nets, devices with their nets which are all clean. This is a tutorial. Thank you for your patience, and I hope we see each other for the next video. Thank you.